The broadcast is now starting. All attendees are in listen-only mode.
Hello, thank you all for joining us in this, which is the third in our series of webinars which discusses LimitState products, their features and their applications. For those of you who haven't attended any of our previous webinars, my name's Tom Pritchard. I'm the host for today's event, and I'll be introducing the webinar and also rounding up at the end. This particular webinar is entitled Slope Stability with LimitState GEO, and it should be providing you with an overview of how you can apply LimitState GEO, our geotechnical stability analysis software, to the modelling and analysis of slopes, both simple and complex. The main part of the webinar itself will run until approximately 10 AM UK time, and just have a bit of time at the end for questions, which can be posted via the chat functionality that is present in the webinar interface that you should see in front of you. We'll try to answer as many questions as we can in the time available, but this isn't always possible, so I do apologise in advance if we aren't able to get to your particular question. I know we've got a mixed audience today. Some of you will have used LimitState GEO before and will be familiar with it. Some of you will be quite new to it. I would ask that anybody who has some very specific questions regarding the software, which might require perhaps a longer or considered answer, to contact us outside the webinar via info@limitstate.com or by telephoning us, and we'll be happy to answer these in detail for you. Our speaker today is Dr. Colin Smith, who is the LimitState GEO Product Manager, and I'll now pass you over to him.
Thank you very much, Tom, for that introduction. Good morning to those of you in the European time zone, and good afternoon and good evening to those of you joining us from elsewhere in the world. As Tom has mentioned, my aim today is to show you how LimitState GEO can be used to solve slope stability problems, and give you a flavour of how it differs from other methods and how to model a number of specific scenarios. So to this end, I'll primarily be using the software to illustrate the key points, but I'll kick off with a few slides at the beginning and at the end for an introduction and summary. As we're focusing on slope stability here, I'll focus on how we use the software to solve these problems, so I may skip over some of the details of how to actually use the software itself, but I hope the process should be clear to all of you. So we'll run through a little bit of introduction to the background to the analysis methods used in this software, and look at how it determines factor of safety, how we can perhaps use it with design codes such as Eurocode 7, and using it with a range of different types of slope stability problems. Before we get into that, I think it's quite useful for those of you not familiar with the company LimitState to give you a bit of background to that. The University of Sheffield has been conducting research into limit state analysis and design and the use of optimization in civil engineering for almost 2 decades now. This company was spun out from the University of Sheffield in 2006 with an aim of making this research available to industry. Now, of course, industry users want not only powerful tools, but ease of use and support, which is exactly what the LimitState can provide. It has a sophisticated testing system in place. That means every time the software is changed, over 800 tests are automatically run to ensure the software does what it's supposed to do. Now, the company has 2 products at present. LimitState Ring, which is used for analysing masonry arch bridges, and the subject of today's webinar, LimitState GEO, which is a computational limit analysis tool for solving geotechnical stability problems. Now, this slide just shows you the range of capabilities of the software. It can model a whole range of geotechnical problems and determine the collapse state for these particular ones. And of course today we're focusing on slopes, so that's the one in the middle of the image. Now, before we look at how the software works, we'll just do a little run through some of the basic textbook theory, and we can pick up on these a little bit later, looking at the same sort of problems in the software. So, simplest type of slope analysis is a translational slip on an infinite slope. You could do a sort of sliding block analysis to determine the factor of safety, which is nice and simply tan of the angle of friction of the soil divided by tan of the slope angle. Of course, that only works for infinite slopes, which there aren't too many of those around. We can use slip circle methods, which work quite nicely particularly for undrained soils. Here, the circular slip surface shape is kinematically compatible, and it is possible, using an energy equation, to determine the factor of safety on strength averaged over the length of the slip surface. However, the slip circle is not necessarily optimal, and in some cases you need a sort of translational component to that slip circle to get the actual optimal mechanism. But the most common method used for slope stability at present is the method of slices. This is what's called a limit equilibrium approach, and it requires a number of assumptions in the analysis to make it work. Normally a slip circle is assumed, and its location is tried at various different points, as shown in the diagram on the bottom right. The slip circle itself is not necessarily kinematically compatible depending on the soil behavior or soil properties, and the analysis is not necessarily statically determinate. What has to be done to make the analysis work is to make various assumptions about interslice forces, and once assumptions are made there, it's then possible to analyze the problem and produce a factor of safety. But generally it works pretty well, and you get a factor of safety on strength averaged over the length of the slip surface. So as I said, this is the most popular method of analysis, and was developed originally to facilitate hand analysis of slopes before we had computational or computers around to make life a lot easier for us. So if we look at the type of software that's available for slope analysis, at the top left we have the sort of what we might call traditional approaches, which automate, for example, the method of slices. But if we want to solve more complicated problems and more complicated geometries or more complicated soil behavior, then we need to move to finite element methods, which typically require a lot more expertise to use. And sitting in the middle is, we think this is where LimitState GEO sits. It's a computational limit analysis program, and it has the advantage of being able to handle any geometry and a whole mixture. You can include retaining walls, foundations, soil reinforcement in a very general way to a slope stability analysis, but you keep the simplicity of the sort of traditional approaches in that you only need the soil strength parameters C and phi, and the unit weight gamma in essence. Now, the software is based on the limit analysis approach. I'll just give a very brief overview of that. In limit analysis, rather than assuming that the soil behavior is perhaps follows this grey curve, which is an elastic phase, then a yield, and then perhaps some post-yield softening, it's assumed to be a rigid plastic material, therefore it doesn't deform until it hits collapse, and then we travel along this red line. As we get deflection, we just mobilize a constant strength. And this allows us to use some very powerful theorems, which are well known. The lower bound theorem: if we can find a state of stress in our problem that is in equilibrium and doesn't violate yield, then we know that's a lower bound to our collapse. Alternatively, if we could find a kinematically compatible mechanism and carry out a work equation analysis on that, we can find an upper bound to the collapse load. And the nice thing about these two theorems is that if we find the optimal lower bound and the optimal upper bound, we find that they match and give us the true plasticity solution. And with LimitState GEO, it uses limit analysis. It actually uses upper bound mechanism approach using a method called discontinuity layout optimization. It doesn't require any additional assumptions, and it can be used to determine the factor of strength over the whole soil domain. And the nice thing about the software is it's usually pretty good at finding the optimal mechanism, so we get very close to the actual plastic collapse load for the problem required. And as you can see from this illustration mechanism at the base, this is an example solution. It's not following a slip circle, nor is it following a translational slip. We're getting a slightly circular slip at the top right-hand side, then meeting an interface of two geological materials, and then the mechanism is diving underneath this retaining wall to give us the overall failure mode as here, which would be quite hard to capture with slip circle type analysis. Now, the software is based on a numerical method called discontinuity layout optimization, and I'm just going to give you a very brief overview of how that works, which will help us when I explain some of the principles of slope stability analysis in a moment. So the method was the outcome of an EPSRC-funded research project at the University of Sheffield, published in 2007 in the Proceedings of the Royal Society. And in concept, it's very straightforward. So a small example is given here. On the bottom left, we have a block of soil loaded by a surface load. We discretize the domain, not using elements, but using nodes. And then we connect every node to every other node with a potential slip line. So here we've got 12 nodes, so we've got 12 times 11, 132 potential slip lines. And then we use optimization to pick out the critical slip lines that form the critical collapse mechanism for that particular process. So the more nodes we have, the more slip lines we have. And we can quite easily solve with 1,000 nodes, so around about 1 million potential slip lines, and out of that set of 1 million, we can pick the critical collapse mechanism. So we can get very close to the optimal result in general. So as I've said, it turns out to be a simple linear optimization problem, and once we've found that critical layout of slip lines, the software will actually put them together to form sliding blocks, so it can animate that to provide additional interpretive guidance as to what the solution is actually doing. So here we've got a two-layer slope problem giving us that solution. As I've said, if we increase the number of nodes in the problem, we get more potential slip lines, and that allows us to devise or find a more precise mechanism. But it gives us quite an intuitive output that we can see sliding blocks, which is often how we like to conceptualize these sort of problems. Okay, well that's enough of the introduction. We'll now just have a look at the software. So when you start up the software, this is pretty much how it looks. We have a number of buttons along the top left-hand side, some explorers and editors, which I'll explain as we go along. To start a project, we just click New, and we can create what's called an empty project, where we can draw the geometry of the problem that we like and import that from a CAD file, or we can use some quick build wizards to quickly generate a geometry. So I'm going to pick the slope stability wizard here, click OK. It runs us through a few pages. First page is just to give the background to the project that we're running, so I'll leave that blank. We can then enter some geometry for the problem. I'll stick with the defaults in this case. If we want a water table, we can put the geometry of that in. We can define the soil type. In this problem, we're only going to have one soil called soil A. I'll stick with the defaults, which in this case would have an undrained soil of undrained strength 50, unit weight of 20. We can have a load if we wish in this case, but we'll miss that out for the moment. We can define partial factors for the problem. I'll skip this stage for the moment, and we'll come back to that later on. And we can choose the analysis type. Now, this software provides us with two analysis types. We've got a factor strength mode, where it will find the factor of strength on the soil required to cause collapse, or you can use a factor load mode, where you select a particular load in the problem and the software will tell you how much bigger that load has to be increased by to cause collapse. For slope stability, we're normally always interested in factor strength, so I will stick to that. We have the nodal density here, so this tells us how many nodes we want to use. There's some broad settings given by default, or we can enter our own value. I'm going to use coarse for the moment, which is 250 nodes. This is primarily for speed of solution, so that I can use the software interactively. But once we've got a particular analysis that we want to check, we would increase the number of nodes and perhaps go to very fine, which gives us 2,000 nodes, and that's around 4 million potential discontinuities in the problem. And click Finish. So, draws me a simple geometry. This is a very steep undrained slope, the type analyzed by Taylor. And in this particular factor of strength mode, the analysis is very simple. We just click Solve. You see the nodes appearing, and very quickly it finds the required collapse mechanism and gives us what's called an adequacy on strength. Now, for the moment, we can treat this as a factor of safety on strength. So effectively, this is equivalent to a factor of safety of strength of 2.47. Now, the software is very easy to change properties. We can deform the geometry like that, get a lower slope, for example, and solve. And we get a different mechanism. This is a much deeper mechanism, like so. We can click an undo button up here to revert back to our original analysis. I'll just resolve that original problem. So we found that we've got a factor of strength of 2.47, which means we have to reduce the source strength by 2.47 to cause collapse. If I just enter this value 50, if I divide 50 by 2.47, it's going to roughly come out as 20. So if I change the strength of the soil by 20 and resolve, I should get an answer of around about 1, which is pretty much what I do. So there, I've tuned the problem so it's exactly at the point of collapse, but normally a slope is going to be safe and have a margin of safety above 1. I can also enter a slightly different nodal density, a medium density here, and that puts more nodes onto the problem. Excuse me. It takes a little longer to solve, and we get a slightly more accurate answer, and here the factor's gone down from about 0.99 to 0.98, so less than 1% difference. But the more nodes we put on, the more accurate the result, but the slightly longer it takes to solve. So I'll revert back to coarse in this case. Now that's an undrained slope problem. We may be wanting to solve a frictional soil problem, so I'll open a file that I've got already, a drained slope here. So this particular problem, if anything I click on in the software, its properties should appear in the right-hand box as property editor. So if I click on this element here, it gives me the properties of this solid body. It gives me the nodal spacing that I can define, but more particularly I'm interested in the materials. I've got one material there called soil A, and in this case we've got a C' of 5 and a phi' of 30 for this soil and a weight of 20. We can define the drainage behavior. In this case it's called drained undrained, and that means the analysis is under control of a global setting, which I can get by clicking anywhere on the blank area of the screen, and it's this setting here, long-term analysis. If it's true, it uses drained properties. If it's false, it uses the undrained properties of that particular soil where it's been defined as drained undrained. So here effectively we're solving a drained analysis with C'5 and a phi' of 30. So again, I just click solve. Now, to know that if we use the method of slices on this method, using Bishop's method, we get an answer of 1.6. In this particular case, you can see that we're getting an answer of 1.63, which is very close to that method of slices result. And of course, the method of slices solution doesn't have a particular status. It's not an upper or lower bound, so we can't really say much more about the comparison except that it's within a 1 or 2%. And when we solve this problem, what the software is actually doing, the limit analysis method is actually optimal for finding factors on load. So what it's trying to do is find the factor on strength, which gives us a factor of load of 1 for the problem. So that means we're trying to say what do we have when we're trying to find factor of load analysis. We're finding how much we have to increase the weight of the soil in this slope to cause collapse, and then we're adjusting the strength until that factor changes to 1. Now we're going to jump to a planar slide problem. If I can find that one, there we go. So here I've got a 35-degree slope of a soil. It's called soil A. All the materials that in the problem that I have appear in this Materials Explorer on the left. So as well as clicking on here to find the properties of soil A, I can also click up here, and that also gives me those properties. So we have a soil that's got a C' of 0, a phi' of 30. It's set to always behave in a drain manner, and a unit weight of 19.5. This body here is set to be rigid, so you can imagine it to be rock, and that's really just to make sure that we're focusing on the surface failure in this case. Now if I click solve in this case, what happens is the software is able to find the solution in terms of a factor of strength. It finds an answer of 0.8379, and the expected answer is expected to be tan of the angle of friction over the tan of the slope, which is tan 30 over tan 35, so it's expected to be unstable. That answer is about 0.82, and software has found an answer of 0.84 roughly, so it's just 1 or 2% out. Now, it's not displaying a failure mechanism because the failure mode, critical failure mode, is in fact an infinitesimally thin layer of soil sliding on the surface. And if we click this button more here, we see that actually what it's been able to do is bracket the answer between two values, what we call locked and unstable. As it's trying to find a solution just between an angle of friction which gives a stable result and an angle of friction which gives an unstable result. For a granular soil, we know that a slope is either stable or unstable depending on its slope angle, and no change in weight of the soil will actually affect that result. So as the software tries to iterate to get to the right solution by factoring load, it's bouncing between these two solutions. If we want to see the mechanism, what we can do is just add a very small cohesion to the soil here. So I've changed the C' to the soil to 0.1, and now we should find that the software will find us this mechanism using the nodes that it's got there. So it's finding a solution that's best made up of slip lines to interconnect the nodes that are available there. So it's finding something that is relatively planar. Clearly this isn't an infinite slope, so we're actually have to meet the top or the bottom of the slope at a point here, but then it's coming out in a planar slope and it's giving us a result which is slightly bigger than the previous result. And you'll see that the animation actually, there's a gap forming here. This is as the soil slides, it's actually modeling dilation, and that's part of the plasticity analysis employed in the software. In plasticity analysis, friction is modeled as dilation. So when you see in these animations for frictional soils these gaps forming, that's perfectly normal. That's part and parcel of plasticity theory. Now normally the software will detect if you're trying to model a soil with zero cohesion, and automatically if the C-dashed value, if it's a frictional soil with a C-dashed of less than 0.1, it will make the C-dashed equal to 0.1 to give you that mechanism. This is set here using this factor strength mode. This artificial cohesion we can set as 0.1, and even though I've set the actual soil property to 0, it actually will do that automatically for me. So there it finds the mechanism. So we've looked at a planar slide, we've looked at an undrained slope problem, and we've looked at a frictional problem. I'll just quickly jump back to the presentation and just show you some results. So clearly you want to know how accurate this method is compared to other methods. So the software has been verified against a wide range of closed-form solutions and benchmarks, and you can view over 100 results on the LimitState website. This is just one example from the slope problem of an undrained slope stability of a 60-degree slope. And we have a benchmark from the literature of 5.25. For this problem, we've got a solution of 5.35, and that's out by about 2% in this particular context. So generally very, very close results obtained. I also got one other graph here of Taylor's stability charts. So you can look up Taylor stability charts in the literature quite easily, and the data points here show the software results which fit very closely to that and actually get better mechanisms down at this transition area for the situation where the soil extends below the toe of the slope. And this is actually seen in more advanced analyses also using other methods. So we'll jump back to the software and look at some more examples. So we'll pretty much be using as our benchmark this drained problem. So if you recall, this is a drained problem with a C-dashed of 5, a phi of 30, and if I solve that problem, I find that I get a factor on strength of around about 1.63. And then the surface slide. Now if I want to do an analysis to a design code such as Eurocode, I can use this feature in the software called the Scenario Manager, and this allows me to define a range of factors on loads and material properties. Now I can type values in, or I can use some built-in values. I'm going to use Eurocode 7 Design Approach 1 Combination 2. This is the Eurocode set of factors that is most commonly used for slope stability. And in this case, the primary thing is that it pre-factors soil strengths by 1.25 for the drained properties and 1.4 for the undrained properties. And it also applies some factors to unfavorable loads. So I'm going to set that value, and having chosen that scenario, that means any analysis I do subsequent to this will pre-apply those factors to the problem. So if I solve now, what I should find is that I get a factor on strength of 1.3, which is equal to the 1.63 I had before divided by the 1.25, which is the Eurocode partial factor pre-applied to the problem. That's what I get here, 1.3. And for Eurocode, all you have to do is show that this adequacy factor here is bigger than 1, and that satisfies a Eurocode. If you've pre-applied the factors, then if this number is bigger than 1, it means that you have to additionally factor the soil strength in order to get collapse. And that's equivalent to showing that the actions in the problem are less than the resistances, for those of you familiar with the Eurocode terminology. And the nice thing about the numerical methods of solving slope stability is that if you're using strength factoring, then you can let the method find the critical mechanism, which is hard to do with a resistance factoring approach. So you can just let the software find the critical collapse mechanism, and as long as the adequacy exceeds 1, the problem complies with the code. Now, sometimes we have loads in the problem. What if we have a surcharge above the slope? We can add a load in there. So if I click on this boundary, you'll see that in the property editor, I get the values of the property, and I have loading here, and I can set a permanent accidental or variable load. I'm going to set a variable load of 5 kilonewtons per meter squared. I'm going to set this to false. This doesn't actually matter in our factor on strength mode. It's not set relevant, but what is relevant here is that it's an unfavorable load. We can make that favorable, neutral, or unfavorable, but we're going to set it as unfavorable. So we've set an unfavorable variable load on the soil surface. And if we look at our scenario manager, we see that unfavorable variable loads get factored by 1.3. So that 5 will be multiplied by 1.3 before the analysis is carried out. And then if I click Solve, now you'll see that a window has popped up called Diagnostics. This is fine, is a very useful feature of the software. So the software, whenever you solve a problem, it has a look at it, checks to see what settings have been applied to the problem, and if something looks slightly unusual, it just flags this up just to give you some assistance in checking that your problem has been set up correctly. So it's simply saying non-unit load factors have been specified in the model. Is that what we really wanted? And have we set our loads correctly as favorable or unfavorable or neutral as required? So I'm happy that that's fine. So we solve that problem, and what we find is that we're going to get a slightly smaller, we'd expect to get a slightly smaller adequacy factor on strength, or factors, which is that extra margin of safety on strength over and above the Eurocode factor of 1.25. So here we've got a value of 1.29. So that surface surcharge has not done a great deal. It's not really contributing to the failure much, because it's the weight of the soil that's giving us the failure. So that's dealing with surface loads. I'll just remove that surface load, and we'll have a look, and we'll just revert for simplicity back to a unit set of partial factors. Clearly, quite often we're going to have water in our problem, so we can apply water pressures by a range of means in LimitState GEO. There isn't time to go into all of them, so I'll just look at the simplest one, which is to draw a simple phreatic surface. So this button down on the bottom left called Water Table, if I click on that, that allows me to draw in a water table into the problem. I can also directly edit the coordinates if I wish. And that is applied in the problem as a simple phreatic surface, common in many slope stability programs. If I click Solve, the software will again solve that problem with that water pressure added in. So if we call the factor of safety on strength for this analysis is 1.6 without the water table, and hopefully we'll get something a little bit lower in this case when it gets through to the solution. It's taking a little while to get there. Yeah. Occasionally we get a result called unknown here, which is when the solver has a problem trying to, the optimizer we use is a third-party optimizer, which is usually very powerful, but occasionally it gets posed a problem which is slightly tricky for it. Normally, just changing the nodes slightly will fix that. But what I'll try here is just moving the water table a little bit and resolving, and just to show you what the result comes out as. Now, as we've moved that water table quite close to the slope, we should get a more significant reduction in strength. So in this case, we've got the adequacy and strength has now dropped to 1.11, so it's 1.6 before, now 1.11, so we've got quite a significant loss of safety for this slope now that we've got that water table quite close to the surface. And it's quite easy to move the water table around different locations if you wish, or to redraw it in a different profile. We'll remove that water table and revert back to the problem. The other common issue is, of course, not all slopes are homogeneous soil, so we'll look at how we can model a layered soil. So it's quite easy just to draw extra elements into the problem here. I'm just using the line drawing tool to draw a line across the problem, and I'm going to leave my original soil up there, but I'm going to take this firm clay, which is going to be modeled as an undrained material with these properties. I'm going to put that down on the bottom layer. You can just drag and drop materials in the software as to where you want it, and then I can solve that problem. So now we've got a two-layered analysis, and the software will find the collapse mode for that. And in this case, we've got a factor on strength of 1.249. So clearly the analysis has changed with that change in material property. Sometimes we find that we've got a homogeneous material, but there might have been a pre-existing slip or a very thin band of weaker material. So we can also apply property materials to boundaries. So I can take, for example, this soft clay, drag it and drop it on this boundary here. I can get it right. So now this boundary has the properties of soft clay, and if I analyze that, I will get, again, a different failure mechanism which is going to make use of that weaker layer, as you can see here. So that's sliding down that, and in this particular case, the adequacy is 1.5, so it's a small reduction from the 1.6 that we would have had without that particular analysis. Just at this point, I'll just show you the report. So when you've done an analysis like this and you want to document that, then you can generate a report for the problem. And this gives you the failure mechanism, the background to the analysis, the data that's within that, what's set up, all the material properties, partial factors employed, etc. And this can be output to a RTF file and edited in Word if required. Now occasionally in the software we get situations where you've imported a geometry from say a CAD drawing, and quite often in those cases you get little steep parts or little undulations in your slope. Now normally that doesn't bother slip circle or method of slices type methods which look for global failure, but this software is designed to seek out the critical collapse mechanism. So if you get something like that, what can happen is it can say, oh well, that's quite steep, actually that's where the failure is going to occur, and ignores the overall failure. So to avoid that, you could either flatten the slope out a bit, because that slope may not really be there, it may be just an artifice of the drawing, and then the software will revert back to finding the sort of global failure mechanism. in this particular case. So we'll get there fairly soon. This is a slightly different geometry to the previous example, so we've got a lower adequacy of strength there. Alternatively, if I click this undo button, if I really want that profile there, I can ask myself, well, why is it really there? It's probably because there's vegetation reinforcing that slope, or there's a stronger material there. I can actually create a little extra zone in here, individual body of soil, and I can create a copy of this soil. I've already done it in this example, but I'll do it again. So if I just click duplicate material, I can duplicate this soil A, which is this copy here, and I've got a C-1 and a phi-30. Let me just say I'll give it a slightly higher C-4 there to assume it's got slightly more strength. And I'll just switch its color so we can see what it looks like. And then if I put that on that area, then hopefully that will give it enough strength that it won't fail locally. Now clearly, if we're analysing a slope and we find that it doesn't have the required factor of safety, then we may wish to improve the slope. So we'll just finish off by looking at a few ways of improving the slope stability. So I'm going to look at an undrained slope here. If I solve that, I find that I get a deep mechanism. So one way of increasing the stability of that, well, I can either reprofile that, we've had a look at doing that before, or I could perhaps add a berm at the base. So if we note the factor of strength here is 1.74, I can use this polygon drawing tool here. Again, I'm drawing this by hand, but you can put in more precise coordinates. So I'll draw in a polygon here sitting on the surface. If I click on that, we can see its coordinates down here, which I could edit. And I'm going to put a dense sand on that to act as a berm and then resolve the problem. So I can see whether that will improve the stability. So it's extended the failure mechanism and it's increased the stability of my problem from 1.74 to 1.9. So some improvement there, and that may be sufficient. And I should add, as I've mentioned before, I'm doing all these analyses with a coarse nodal density. When I want to do my final precise analysis, I should increase that number of nodes to get the a more accurate, a more precise answer. Now, an alternative way of increasing stability is to perhaps to insert a retaining wall. So here's the example I've used many times before of this drained slope with a factor of strength of 1.6. If I want to put a retaining wall there, let's say I want to put one in halfway up, I'm going to use this line tool here. I shall click there and come down to that point. And I can use what's called a engineered element in the software which can be applied to boundaries. So I've set a boundary here which is the location of where I want to put a retaining wall. I need to create that, so I'm going to use Tools, Create New Material, and I use this thing called an engineered element. I will call that a wall, and I'm going to use a rigid sheet pile wall. If I use that, I don't need to enter any properties here. there isn't time to talk about these properties, and in fact the use of the engineered elements, which are essentially used to model a whole range of different soil reinforcement types, including sheet pile walls, is the subject of a future webinar. But we'll use this rigid model here, click OK, and now we've got a wall here. I will drag and drop that onto this element here. Now I've got a retaining wall sat in the middle of my slope. I will analyze that problem and see if that has any influence on the strength. So what you can see is that the failure mechanism has had to go deeper. The wall will fail by rotation, but the factor of strength has gone up to 1.9 from 1.6. So that's had a reasonably good effect. And it's quite easy to see what the effect of changing the depth of the wall is. If I reduce the wall length to be very short, then what should happen is that the failure will just go around the wall and it will have no effect. So we should get an answer of around about 1.6 again. And you can see the wall just moves with the soil, has no great influence. So I need to make it at least at this kind of depth to start to have an effect, to start to cause that failure mechanism to get larger. So there we've increased the strength from 1.63 to 1.66, not a huge gain, but you can see how we can change the length. So it's quite easy to do all sorts of what-if scenarios with the software quite interactively. We can put in different wall types at different locations, we can add berms, we can reprofile the slope and see what effect that has on our analysis. If I get rid of that slope by clicking this undo button, so that removes all those items. Another way I can reinforce a slope is to actually add something like a soil nail to the problem. Again, description of this in detail is beyond the scope of this presentation, but I will create another engineered element, which I will call nail, and I'm going to use a rigid soil nail model. Now we can define various properties, pull out factors, etc. As I said, I haven't got time to go into the details of these properties, but I shall put in some reasonable values here for those factors. And I can now add a nail to the problem. Again, these things get added to boundaries, so if I want to have a nail, say, halfway up the slope, I could perhaps put a line in here. I can add a vertex down here so that I can use this part of the boundary for my nail, and then I can drag and drop that nail to there. And then I can click Solve and see if that has any effect on the stability of the slope. So it's had a reasonable effect. We've increased the slope stability factor and strength to 1.77. The slope is able to slide, as it were, past the nail, but the nail is imparting tensile forces into that soil, which is being transmitted back through the nail, and this graph actually shows the axial or tensile force in the nail being transmitted back to its endpoint. So that is actually reinforcing it, and if we put more of these in, we would get more reinforcement. And again, we can look at what difference it makes if we change the length of these things. So if I make this much shorter, we would probably expect the mechanism just to go around the nail or to pull the nail with it rather than the nail staying where it is and the slope sliding past it. So it's just moving with the slope and hasn't really had a great effect on the stability. So that gives us, I hope that's given you a good flavor of how you can use the software to solve slopes, how the results that it gives, how we can use the software to change, to do what-if analyses, and to look at adding reinforcement elements or regrading the slope or different ways of trying to increase the stability of the slope. I'm just going to quickly revert back to the presentation to wrap up, to give you a summary. So I hope you've seen that the method discontinuity layout optimization is as straightforward or more so to use than the conventional method of slices, which is the most common method for slope stability. Because it uses plasticity theory and seeks out the most critical mechanism, there's no need to specify entry-exit points, a solution method, interslice force functions, or a search space. It will just find that critical solution depending on the number of nodes that you specify in the problem. And it automatically searches all possible failure modes, so it can find a highly non-circular slip failure or slip mechanisms that you didn't expect. And this mechanism on the right here is quite a nice illustration of an embankment on where a layer of weak soft clay in the middle, and that's actually undergoing squeezing, an extrusion, which would be quite hard to model using a sort of slip circle type approach. I hope you've also seen that it's quite flexible in terms of modeling the slope geometry and low definition, and that we can add in retaining walls or equivalently piles or reinforcement into the problem to see if that will assist in stabilizing the slope. Built-in wizards for quickly defining these problems. It's very easy to define partial factors, and we can specify water table. You could also do RU coefficient analyses. I wasn't time to look at those, but that's fairly straightforward in the software. And you can get a comprehensive report output in terms of what's been achieved. So I hope that's given you a good overview of the software, and that you can see that it's very easy to use interactively to answer what-if type questions, and empowers you really to get a better feel for the problem, to explore the problem, to see what different parameters have. And it can not only solve slope stability problems, but you can solve any other problem, retaining wall, foundation, etc., without having to try and impose idealizations or corrections to make your problem fit a particular problem type. So with that, I'm going to wrap up and invite some questions. So we have a few minutes for questions. Oh, don't seem to have any questions at the moment, so what I'll do is I'll just pass over to my colleague Tom to wrap up this session, and then if there are questions afterwards, then I can pick up on those. Okay, over to you, Tom.
Thanks, Colin, and thanks everyone for attending. As Colin said, now we're near the end of the webinar, so I hope you found it useful. For people who are current users of the software, we hope that you learned something new about it and maybe that you didn't already know. But if the webinar has prompted any questions, please get in touch via the telephone or support@LimitState.com, and we'll be happy to answer any questions that you may have. For people who aren't current users of LimitState GEO, we'll be in touch over the next few days to get some feedback from you, find out if you have any further questions, and to see whether you think LimitState GEO may be useful to you. Just a note, if you'd like to watch the webinar again, or if you think you might know a colleague who would be interested to see it, there'll be a recording available later today for you to download and watch again. We'll send you an email with a link once it's available online. Everyone here may also be interested to know that there are a number of other scheduled webinars dealing with LimitState GEO and its applications. I think Colin mentioned them earlier. So please look out for the event notifications that will be sent out via email and also posted on our website at www.LimitState.com/events. Finally, I'd like to say thank you all for listening, and I hope that you can join us again for one of our future sessions. Thank you.
Okay, thank you, Tom. I'm now seeing a whole number of questions are now pouring in, so I'll try and pick out a few of those and answer those in the next 5 or 10 minutes. Okay, question, can you get a trial version to evaluate? The answer is yes, you can download the software from the website, and that comes with a trial license, so you can use it straight away. I have a question about a modeling tension cutoff. You can model tension cutoff in the software, so what I'll do here is look at a undrained slope problem, analyze that first as is, factor and strength of 4.63. You can add a tension cutoff material, there's a material here, to the whole soil body, and if I click add here, then I get the checkerboard pattern which shows I've got two materials in here, effectively my original soil, my cohesive soil, and another material which imparts an additional tension cutoff property to that soil. So if I click solve here, first thing I get asked is unit weight. I've actually put two materials into the same area which have different weights. The no tension cutoff material I'm using is 0 weight. I want to use the maximum value here, which is the original soil weight. And then the software should find me a mechanism which will include potentially having a tension crack in the soil. And you can see tension cracks opening up here, slightly off vertical, but that's the way the stresses work out in this particular case. So you can model tension cracks either in the soil body, or also if you have a retaining wall or any other structure, you can add these no tension cutoff materials to boundaries so that you can get breakaway of, let's say, a wall from a soil body. A question about material laws. Essentially, the soil model that's being used in this software is more Coulomb. So whenever we define a material, most of our materials, if I create a new material here, are more Coulomb materials. So we're using C-phi and Cu, and we're using the more Coulomb for C-phi materials, and essentially Tresca for Cu as our failure condition in those. So it's the standard sort of models for soil behavior, but you can modify them as we've just shown by adding a cutoff material to eliminate tensile strength in the solution. Just picking up on more questions. Apologies, I'm just having trouble scrolling through these questions. Right, I had a question about stage construction. In essence, this is an ultimate limit state analysis. So while you can model stage construction, because it's looking for the collapse state, in plasticity theory, the initial conditions do not affect the failure mode. So doing a stage construction, you would have to explicitly set up any particular changes which might arise from the stages in that analysis. But if you want to build up the problem in stages by adding extra geometry, that can be done, but that may not be the aim of what you're looking at. Okay, I had a question about why I don't mention factor of safety, but factor of material strength. In most slope stability analysis, we're primarily interested in the factor of safety, which is defined as a factor on strength. And it's very important to be clear what the software is doing here. So it's finding the factor on the soil strength that is required to cause that system to collapse, which is conventionally viewed on as a factor of safety on strength. But if you're analyzing, for example, a foundation, so if I just run a very simple foundation model here, in this particular problem, I've got a load on my foundation and I'm using a factor load mode here, and the software can be used to give me a factor on load. and that's a factor of safety on load. So when I'm talking about factor of safety in this particular, in the slope context, it's factor of safety on strength, but for foundations we might be more interested in factor of safety on a load. So these are all margins of safety on a particular parameter. Okay, something about question about extent of boundaries in respect of the problem geometry. So if I were to run a shallow slope stability problem like this, you can see that the mechanism touches the bottom of the problem domain. Now, if that's not a real boundary, if that's just an artificial boundary, because obviously we can't draw infinite boundaries generally in numerical software, if that's not a real boundary, then that mechanism has been constrained by the boundaries and is not valid. And what you would have to do is move that boundary downwards. So I can move that boundary downwards, and the mechanism now doesn't touch the bottom, but now it touches this left-hand corner. So again, it's not valid, and what I would have to do is move that boundary out. I'm just going to switch to coarse number of nodes to speed that up. And what we'll find, actually quite interestingly in this particular case, is that no matter what I do, this particular mechanism will always hit a boundary, and that's the reason is that for a shallow slope and an undrained soil, the actual critical mechanism for an unbounded body of soil is a circular mechanism like this of infinite radius. So in this particular case, no matter how much I move these boundaries out, I'm onto a loser really, so it's not going to help. But generally, when you're looking at slope failure mechanisms, if they touch the boundaries, unless those boundaries are real, if they're rock, for example, then the analysis is not correct, it's constrained, and you need to move those boundaries out. Question about, is there any hardening behavior available? Not in plasticity analysis. In this analysis, we're adopting a rigid plastic model, so it's a rigid material until it yields, and then it yields at constant strength. In order to do hardening behavior, you need to go into an elastoplastic finite element model in order to model that correctly. And obviously, it's an extra degree of sophistication in achieving those results. But this software is designed to give you very quick and easy analysis tool, following the pattern of many conventional analyses. Let me look at other questions. Okay, question about, can we model a problem where the soil is potentially affected by preload in anchors? Again, I think this comes back to plasticity analysis. That's the kind of initial condition. So at plastic collapse, a preload should not have an effect on the collapse. You could look at preload in advance if you wanted to see if it would cause your anchors or whatever to move, but if they don't move, then that effectively is an initial condition which should be affected by a purely plastic analysis. I've got a question about modeling soil flow between piles for reinforcement. So if I have I'll just bring up one of those models with the wall in. If I want to treat this wall not as a sheet pile wall, but as a pile, so if I'm going to put piles into the wall that have a reasonable spacing, I can actually get the software to model flow around that pile by treating the pile as effectively as a soil nail. And I have in the properties for that a thing called a lateral factor, which is basically the lateral resistance of that engineered element to soil moving past it. those have to be put in as explicit values. So because it's a plane strain software program, it won't work out what that is from the diameter of the pile, etc. You'd have to put that in. It's relatively straightforward for a cohesive soil. For a pile that's deep down, it's going to be round about 9 to 12 CU. For a frictional soil, it's a little more tricky to calculate, but if you're happy you've got a conservative estimate of what that lateral resistance would be, you can apply that to that pile. And if it's going to be slightly different higher up than lower down, you can just split it into two and set different properties for different halves. Okay, got a question about interfaces between a wall and a nail in the soil. In this particular case, if I click on this element here, you'll see the properties appear up here. The materials are defined as the engineered element, which is the wall material that I defined, but I also have a right material and a left material, and so I can actually define boundary materials on that wall. So if I want that wall to be frictionless, I can assign, for example, a frictionless soil. So if I click the change button there, I'm able to pick from a choice of materials there. In this particular file, I don't have a frictionless soil available, but if I wanted to put, for example, the properties of a very soft clay onto the boundaries, I can do that there. And if I sorry, I've replaced that. Didn't mean to do that. Okay, I can set, for example, the right-hand boundary of that material to be a very soft clay. So that basically means the interface between the wall and the soil now has this property. So normally I'm going to set that to perhaps 2/3, a half of the adjacent soil property. So it is quite straightforward to do that and to model that correctly. Just scanning through the questions again. I think we'll just look at one more question. So there was a question about looking at lateral soil pressures in the wall. This is, of course, getting slightly into soil, into wall interaction around the slope stability. If the wall itself interacts with the soil significantly, and the easiest thing here is to actually pull up a sheet pile wall model wizard, just use a default. So here we have a sheet pile wall in cohesive soil. If I click solve on that, it finds the collapse mechanism for me. And because it's an undrained soil, I get a tangent crack opening up by the wall, and here it's able to display axial force, shear force, and particularly the bending moment in the wall due to the applied stresses. And those can be exported to a CSV file for further analysis. So you can pick out stresses in that case, but they're only valid where the wall is collapsing with the soil. In ultimate limit state analysis, the key parts of the analysis is where the collapse is going on, and these are values at the ultimate limit state, and you obviously have to remember that they may be less critical than those at serviceability limit state, but they can be extracted. So in some conventional analyses you would use these directly, and they can be extracted quite straightforwardly from the analysis. Okay, well we've run on 10 minutes there, and I think we'll draw that session to a close. So if I can thank you all for your attention, and hope you've learned something useful from this. And as Tom has said earlier on, if you do have any specific questions, feel free to email those through. to LimitState, and we will try to deal with those as they come in. So thank you very much for your attention, and I hope you'll be able to join us for one of our later seminars. Thank you.